Welcome to our deep dive today. We're going to be exploring some really cutting-edge research on how AI is learning
Okay.
to reason like us humans, even without mountains of labeled data.
Interesting.
Specifically, we're going to unpack a research paper
Okay.
called Diving into Self-Evolving Training for Multimodal Reasoning. This mouthful, I know,
Yeah.
but it's really a fascinating look at how large multimodal models,
hmm
or LMMs, are being trained to think more effectively.
It's a really exciting area of research. You see, the challenge with training these models is that they need to be able to make sense of different types of information, like text and images, and connect them in a
Right.
way that makes sense. Think about how you solve a math problem. You use the words in the problem and any diagrams
Uh-huh.
to reach a solution. That's multimodal reasoning. And it's not easy to teach a machine to do that.
So it's not just about understanding words or pictures separately.
hmm
It's about connecting the dots between them.
Right. Right. And the traditional approach to training AI models relies on a lot of human annotated data, where we label every piece of information. That can be incredibly time-consuming
Yeah.
and expensive, especially when you're dealing with the complexities of multimodal data.
So how are researchers tackling this challenge? That's where this concept of self-evolving training comes in, right?
Yes, self-evolving training is inspired by the idea of reinforcement learning, where models learn from their own mistakes and successes.
Hmm.
It's like a student revising their own work based on feedback, gradually getting better over time.
Okay.
In this case, the AI models generate responses, receive feedback in the form of rewards, and then use that feedback to refine their reasoning process.
So it's almost like independent study for AI, learning by doing instead of just being spoon-fed information.
It is, and what's really cool is that this paper lays out a specific framework called MSTaR, which stands for Multimodal Self-evolving Training for Reasoning, that researchers developed to optimize the self-evolving process.
Okay, MSTAR, let's break that down. What makes it tick?
MSTAR has three main components that work together. First, there are the training methods. The researchers focused on continuous self-evolving training, where the model learns progressively, building upon what it learned in previous iterations.
Okay.
Imagine a runner who doesn't stop to catch their breath between laps, allowing for faster progress.
So it's like giving these models the ability to build on their past experiences, making their learning process much more efficient. What's the second component?
The second component is the reward model. Now, this isn't just about checking if the AI gets the final answer right. It's about providing more nuanced feedback on how it arrived at that answer.
Okay.
It's like having a thoughtful mentor rather than a strict grader.
So not just a pass or fail, but feedback on the thought process itself.
Yes. The researchers introduced a novel approach called the process reward model, or PRM, which specifically rewards the quality and relevance of each step in the reasoning process, not just the final answer.
All right, continuous learning and this PRM for better feedback. What's the third piece of the puzzle?
The third component is prompt variation. During training, they used both labeled prompts, which have clear answers, and unlabeled prompts, which don't. This helps the model learn to generalize its reasoning abilities to a wider range of problems.
The unlabeled prompts, that seems tricky. How do you guide the model if there's no right answer to compare it against?
That's a good question. Researchers use techniques like weighted voting to generate pseudo-labels, essentially making informed guesses about the answers for unlabeled prompts. It's like crowdsourcing a solution from multiple perspectives.
It sounds like they're really trying to mimic the kind of messy real-world problems that AI will need to solve in the future, where we don't always have clear-cut answers.
That's right. And one of the key insights from the research is that this whole process of self-evolving training isn't static. Models need to balance exploring new reasoning paths with exploiting what they've already learned.
That tension between exploration and exploitation, trying new things versus sticking with what works, that seems like a fundamental challenge in any learning process, whether it's AI or human.
It is. And to monitor this dynamic, the researchers used a few key metrics. One is greedy accuracy, which measures how good the model is at picking the most likely answer based on what it already knows.
So how well it can exploit its existing knowledge. What about measuring its ability to explore new options?
They use something called pass at K accuracy, which looks at the chance of the model finding the right answer within K attempts. This gives you a sense of how effectively it's exploring different possibilities.
And I imagine there's a trade-off there. You want to be good at both exploiting what you know and exploring new possibilities. What did the research reveal about this balance?
One of their key findings was that as models got better at exploiting what they knew, greedy accuracy increased. Their exploration ability tended to decline. It's like getting stuck in a rut even if you're good at what you already do.
So how do you encourage the AI to keep an open mind and not get too stuck in its ways?
The researchers found they could maintain a better balance by dynamically adjusting a parameter called temperature, which controls the randomness of the model's exploration.
So making sure the AI doesn't get too comfortable and keeps trying new approaches. What was the overall impact of this MSTAR framework? Did it actually lead to better performance?
Yes, it did. MSTAR achieved impressive performance across several multimodal reasoning benchmarks, including MathVista, M3COT, MMSTAR, MBench, and AI2D, which cover a wide range of reasoning tasks involving both text and images.
And it wasn't just limited to one type of model.
It wasn't. They saw improvements for models of different sizes. Larger models, like MiniCPM v2.5, saw more consistent improvements, likely due to their broader learning capacity. But the core principles of MSTAR held true across the board.
So it seems like this self-evolving training approach has the potential to significantly enhance the reasoning abilities of AI, regardless of the model size. That's pretty exciting.
It is, and it's important to remember that this is a relatively new area of research. We're just beginning to understand the potential of self-evolving techniques.
Now, we've talked about the big picture of MSTAR, but I'm curious about some of the specifics. The paper dives into quite a bit of detail about the actual training process. What were some of the interesting things they discovered about optimizing this self-evolving approach?
One interesting thing they looked at was how they initialized the model for each round of training. Some previous research suggested that starting from scratch each time could help prevent the model from becoming too specialized to the training data.
So kind of like starting with a fresh perspective each time, to avoid getting stuck in a rut.
Exactly. But the researchers in this paper found that continuing from where the model left off in the previous round actually worked better.
Interesting. So building on that accumulated knowledge was more beneficial than starting fresh.
It seems that way. They also explored the idea of continuous learning, where they didn't reset the optimization process, the way the model refines its parameters, between each iteration.
So it's like keeping the momentum going instead of starting and stopping. With each new set of data,
It is. And they found that this continuous optimization led to significant improvements, especially when testing the model on problems it hadn't seen before.
it sounds like a lot of trial and error went into figuring out the best way to train these models.
It did. They also looked at the impact of changing how often they evaluated and updated the model during training. They had to find the right balance. Too often, and the learning process could become unstable, but too infrequent, and the model might not adapt quickly enough.
So a delicate balancing act to ensure that the model was learning steadily and effectively. Now, earlier we talked about how important this process reward model, or PRM, is for providing feedback on the model's reasoning process. The paper goes into quite a bit of detail about how they actually trained this PRM. It's pretty clever. Can you walk us through that?
They started by training a separate, more mature model on a large set of multimodal reasoning examples. This expert model was trained for a longer time to ensure it achieved a high level of performance.
So it's like they created a gold standard for reasoning to guide the training process.
You could say that. And then they used this expert model to create a new data set. But this time, instead of just focusing on the final answers, they broke down the reasoning process into individual steps.
So instead of just knowing if the AI got the answer right or wrong, they could see how it arrived at that answer, step by step.
Right. And they had this expert model actually annotate each step, indicating whether it was a logical and relevant part of the reasoning process.
So it's like having a teacher grade each step of a student's work, providing feedback on the entire thought process.
It is. And they used this data set of annotated steps to train the process reward model.
So by learning from this expert model, the PRM was able to recognize the patterns of good reasoning. That's pretty ingenious.
It was a complex process, but it was essential for creating a reward model that could give the kind of detailed feedback necessary for the AI to really improve its reasoning skills.
It's amazing to think that we can now train AI to evaluate not just whether an answer is right or wrong, but also how it got there. It's like teaching them to think critically and explain their reasoning.
It's a huge step forward, and it has the potential to lead to AI systems that we can better understand and trust. Now, throughout this deep dive, we've been talking about how well this MSTAR framework performed on different multimodal reasoning benchmarks. But what does good performance really mean in this context? How do you measure the success of these self-evolving models?
That's a good question. I imagine it's not just about memorizing the answers to specific problems.
It isn't. It's about being able to apply what the AI has learned to new unseen problems. In the world of multimodal reasoning, that means being able to take information from different sources like text and images and use it to solve problems
Hmm.
it hasn't encountered before.
So how did the researchers evaluate this ability to generalize what the AI had learned?
They tested the models on two types of problem sets. The first set included problems similar to those the model had seen during training.
Okay.
The second set included problems that were more diverse and challenging.
So they were testing the AI's ability to not only remember what it had learned, but also apply that knowledge to new situations.
You got it. And the MSTaR framework consistently did better than other approaches on both the familiar and the unfamiliar problem sets.
That adaptability is really impressive. It suggests that the AI is really developing an understanding of the concepts, not just memorizing answers. Now, the paper also talked about some challenges they encountered during the self-evolving training process. One was this tension between exploration and exploitation. But they also highlighted the risk of overfitting. Can you explain what overfitting is and why it's a problem?
Overfitting is a common challenge in machine learning. It happens when the model becomes too focused on the specific training data it's been given. It's like memorizing the answers for a test instead of truly understanding the material.
So it can ace the test on the questions it's seen before. But it struggles when faced with something new. How do you prevent that from happening in self-evolving training, where the model is constantly learning from its own outputs?
One important strategy is careful data management. The researchers made sure that the training data was diverse and representative of the real-world problems they wanted the model to be able to solve.
Yeah.
They also used techniques to evaluate how well the model performed on different subsets of the data to make sure it wasn't becoming too specialized to any particular set of examples.
So they were making sure the model wasn't just cramming for a specific test, but actually learning the underlying concepts.
And they also used techniques to prevent the model from becoming too complex. These techniques help ensure that the model focuses on the core concepts, rather than getting bogged down in the specifics of individual examples.
It sounds like striking the right balance is crucial, allowing the model to learn from its own outputs without becoming too rigid. Or too specialized do these strategies work?
They did. The researchers were able to minimize overfitting and ensure that the AI could generalize what it had learned to new problems.
Now, throughout our deep dive, we've been focusing on the technical side of this research, but I think it's important to pause and consider the bigger picture. The ability of AI to reason about the world around us,
Where?
using multiple sources of information, that has the potential to be truly transformative. It makes you think about all the ways this technology could be applied in different fields.
It does. Imagine robots that can work alongside humans, understanding both what they see and what they're told.
Right. Or self-driving cars that can navigate complex situations, not just following pre-programmed rules, but actually reasoning about what's happening around them.
Yeah. And in healthcare, think about AI that can analyze medical images, patient records, and even genetic data to help doctors make more informed diagnoses and treatment plans.
It's an exciting time to be working in this field. And what's remarkable is that all of this is driven by the AI's own outputs. We're not relying on humans to label every single piece of data. It's learning to teach itself. That's incredible. It really highlights the potential for AI to continue to learn and grow independently. Now, one thing that caught my eye in the paper was this idea of skyline experiments. Can you tell me more about those?
The researchers wanted to understand the challenges of training with unlabeled data. Unlabeled data is abundant, but it's difficult to use effectively because we don't have the answers up front to guide the model.
We talked earlier about techniques like weighted voting to generate pseudo-labels, but those are essentially educated guesses.
That's right. So in these skyline experiments, the researchers actually had access to the correct answers for the unlabeled data, but they didn't use them during training.
So they intentionally withheld that information to see how the model would perform, without those clear-cut answers.
They found that even with those answers hidden, the model still struggled to effectively utilize the unlabeled data.
It seems counterintuitive. Even when we know the answers, teaching an AI to learn from them without explicitly providing them is hard.
It underscores just how complex this self-evolving training process is. The AI has to figure out how to learn from its own errors, and that's no easy feat.
And what role did the process reward model play in these experiments?
Even though the PRM wasn't trained on the specific unlabeled examples, it was still able to provide valuable feedback that helped the model learn.
That's fascinating. So the PRM, with its focus on evaluating the reasoning steps, could offer insights even in situations where the model didn't have the right answers up front.
It shows just how valuable it is to build reward models that focus on the process of thinking rather than just the end result.
As we wrap up our deep dive, I want to turn the conversation over to you, the listener. What are your thoughts on what we've discussed today?
What are some of the key takeaways that resonated with you? What questions are you left with?
We encourage you to explore the research paper in more detail and continue to follow the developments in this exciting field. The world of AI is constantly changing, and self-evolving training is undoubtedly one of the most promising areas of research.
It's been a pleasure diving into this research with you today.
Thank you for joining us on the deep dive. We look forward to exploring more groundbreaking research with you in future episodes.